So far in the last lecture, we have studied the different types of number systems and how to convert a decimal number into a different base number system. Now, it was the last example where we have converted 153 decimal number into an octal number, and the process to convert any decimal number into a base R number system is directly by the division process. Now, Now the next topic is the conversion of a decimal fraction to a base R. Suppose we have any fraction number and we have to convert it into the base R number system. So in generalized way, we'll study the algorithm, whatever it is, then it will be followed by some examples to convert a base fraction number into different types of number system. So let us suppose the conversion of a fraction, decimal fraction f into a base R number can be done by successive multiplication by the R. While in the case of integer number, we were dividing the number by base R. In case of fraction, what we do, we'll just multiply the fraction by the base R. R may be 2, R may be 8, R may be 16 in case of the hexadecimal number. Then again, to see how this works, consider a fraction general number. Suppose f is given by point coefficient r minus 1, a minus 1, a minus 2, and a minus m. This is the decimal point, and we have to convert it into base R system. Now this particular number is represented by a coefficient multiplied by r to the power minus 1 plus coefficient, second coefficient multiplied by r to the power minus 2, then a minus m, that is the last coefficient multiplied by r to the power minus m. Now calculate f into r. What we have to do, we are given fraction f, that is suppose 0.512, whatever it is. So we have to multiply this fraction by the base r. R is the base that is of the required number system in which we have to convert that particular number. So suppose if we are converting into the binary number, then what we have to do, we have to multiply the given fraction in the decimal by 2. Then it will be like this, a minus 1, that is the first coefficient, plus f of f1, where the fraction part of the result is f1, and we will get some coefficient, we will get some integer, that is a minus 1. This integer may be 0 or may be any number. If it is the case of 0, then we'll consider 0. Now again, in the next step, we multiply this particular f1 by the r. So f1 by r, and we get again some integer and some fraction part, and this process continues until we have a sufficient number of digits. So in generalized way, we can say that when we have to convert a decimal fraction into a base R number system, then what we do, we just multiply that particular fraction part by the base R, and we keep aside the integer part, and the remaining fraction part is again multiplied by the base R, and this process continues until we get fraction, either a fraction 0 or we have sufficient number of digits. Now let us take an example. Suppose we have to convert 0.6875 base 10 into binary number. So here the required base R is binary number is 2. So what we do, we just multiply 0.6875 multiplied by 2, and we'll get 1.3750. Now this integer part is your first coefficient a minus 1. Again this 0.3750 is multiplied by base 2, and we get 0.7500. Now the next integer is 0. Here we have put it a minus 2 is 0. Now the fraction part is 0.7500, which is multiplied by 2, and we get 1.500. So the next coefficient is 1, and the fraction is 0.5. Again this 0.5 is multiplied by 2, and we get 1.00. Now the fraction is 0. Now we need not to multiply further. Now the next coefficient is 1. So the number is converted like 0.6875 base 10 is equals to 0.1011. This is the coefficient a minus 1. This is coefficient a minus 4. In this way, we can convert any decimal number, any decimal fraction number into any binary, any base of any number system of base r. Now take some other examples. Suppose we have to convert 27.315 to binary number. So here we have two factors. 127 is your integer part and 0.315 is your binary part. So we have to convert both sections or both factors separately. Now to convert the 27 into the binary number, the required base is 2. So first we will convert 27 into the binary number. Now the process is by the successive division. So 27 divided by 2, we get 13 plus 1. 1 is the remainder, that is the first coefficient. Then again 13 is divided by 2. 13 divided by 2, 6 plus 1 is the remainder. Again 6 is divided by 2, 3 plus 0 is the remainder. Now 3 is divided by 2, 1 plus 1 is the remainder. Now again this 1 is divided by 2, 0 plus 1 is the remainder. Now we get integer quotient is 0. Now we need not to further divide it. So 27 is nothing but 11011. This is your MSB, this is your LSB. In the same manner, so 27 base 10 is equals to 11011. That is the binary number. Now we have to convert 0.315 to the binary. So in the fraction part, what we do, we just multiply the fraction part by the base, and the base required base is 2. So 0.315 multiplied by 2 is equals to 0.630. So first coefficient is 0. Again 0.63 is multiplied by 2, we get 1.26. So next coefficient is 1 and the fraction is 0.26. 0.26 multiplied by 2 is equals to 0.52. So the next coefficient is 0 and the fraction is 0.52. Again 0.52 is multiplied by 2, that is equals to 1 plus 0.04. So the next coefficient is 1 and the fraction is 0.04. Now at this moment, as we are seeing that this is not going to be 0, we can stop here and the resulting value will be approximate conversion. So we write here 0.315 base 10 is approximately equals to 0.0101. Here is this is your first coefficient, a minus 1, a minus 2, a minus 3, a minus 4, and we have represented type point a minus 1, a minus 2, a minus 3, a minus 4 base 2. So this value is approximately equals to 0.3125. So in a whole, we can represent the number 27.315 is approximately equals to 11011.0101 base 2. In this manner, we can convert a number into any number system, provided that the base is given, required base is given. For the case of octal number, the base will be 8, and for the hexadecimal number, base will be 16. Again, take an example. Suppose we have to convert 0.513 to the octal number. So again, it is a fraction. Then for the fraction part, we have to just multiply the fraction by the base. And for the octal number, base is 8. So 0.315 multiplied by 8 is 4.104. So the integer, that is the first coefficient, will be this 4. Now again, the fraction 0.104 will be multiplied by 8 like this. Now here the coefficient is 0. Again 0.832 multiplied by 8, it gives 6.656. Here the coefficient is 6. Next 0.656 is multiplied by 8. Here the resultant is integer part is 5.248. Now we can further multiply 248 by 8. Then we'll get 1.984. Again 0.984 multiplied by 8, it is 7.872. Now, the answer to the 7 significant figures is obtained from the integer part of the product, like 0.513 base 10 is equals to 0.406517, and we have put it dot dot because the fraction is not 0 here. When the fraction is 0, we need not to the successive dots. Now here are some number system with different bases. Suppose we have a decimal number 0 to 15. Now in the binary, 0 is represented by 0, 0, 0, 0. So to represent 15 numbers, we need 4 bits. Here the bits are, so it is 0, 0, 0, 0. 1 is represented by 0, 0, 0, 1. Then 2, 0, 0, 1, 0. 3 is 0, 0, 1, 1. 4 is 0, 1, 0, 0. 5 is 0, 1, 0, 1. And for the 15, it is 1, 1, 1, 1. Like this. And for the octal number, as a base is 8. So we have the digits from 0 to 7. After 7, it will be 1, 0. So the 8 will be represented by 1, 0. Then 1, 1 is 9. 1, 2 is 10. 1, 3 is 11. 1, 4 is 12. 1, 5 is 13. 1, 6 is 14. 1, 7 is 17. Now to write the 16, we'll write here 2, 0. Now the 2, 0 in base 8 is 16. In the hexadecimal number, we have 0 to 9, 10 digits. And A, B, C, D, E, F are further represents 10, 11, 12, 13, 14, 15. Now the 15 is F, 10 is A. 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. And all letters must be in capital. So in the upcoming lectures, we will concentrate only 3 number systems, that is binary, octal, and hexadecimal. So these are the number system which are used in your computer or computer any digital manipulations or the calculations. So we continue the number system, different number systems now. Now, based on the previous table, which represents the decimal number, binary number, octal number, and the hexadecimal, in the previous phase, the number system can be easily transformed between each other. We can convert one number system to the another number system. So here in this slide, we are going to convert the conversion between binary to octal, octal to binary, binary to hexadecimal, hexadecimal to binary, and this. Now suppose we have a number 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0.1, 1, 1, 1, 0, 0, 0. Like this is a sequence of the binary number, and we have to convert it into the octal number. So to represent an octal number, we require 3 bits because the base is 8, then 2 raised to power 3 is 8. So here we can find out how many bits are required to represent a particular number. So what we do in this case, we just make the pair of 3 bits starting from the decimal point. So for a decimal point, here are 3 bits. We'll move from the left side, 3 bits, 3 bits, 3 bits, and here are only 2 bits, so we can prefix a 0 here. So for the fraction part, we will start from the decimal to the right hand side, 3 bits, 3 bits, 3 bits, and 3 bits, like this for any number. So we just write the binary equivalent of these combinations. Then 0, 1, 0 is 2, 1, 1, 0 is 6, 0, 0, 1 is 1, 1, 0, 1 is 5, 0, 1, 1 is 3, 1, 1, 1 is 7, 1, 0, 0 is 4, 0, 0, 0 is 0, and 1, 1, 0 is 6. So this particular number is just equivalent to 2615.3.7400. So in this manner, we can convert any binary number to the octal number. Just what we need to do, we have to make a pair of 3 bits starting from the decimal point to the left hand side and from the decimal point to the right hand side. Left hand side is the integer part and the right hand side is the fraction part. So we can directly convert. We need not to do any mathematical manipulation, either multiplication or division. We can directly convert binary number to the octal number. So here the number is 26153.7406 base 8. Now when we have to convert binary number to the hexadecimal number, so for the hexadecimal number base is 16, then the 16 is represented by 2 raised to the power 4. That means we require 4 bits to represent a hexadecimal binary number into the hexadecimal number. Suppose a number is given like this. So what we do, as we require 4 bits in the same manner as done in the octal number, we'll make a pair of 4 bits from the decimal to the left hand side and to the right hand side. Suppose this is your, so 1 1 0 1 4 bit, then again 4 bit 4 bit. Here we are left only with 2 bits, so we can prefix 2 zeros here. So it will be 0 0 1 0. In the right hand side again, this is another example. Right hand side, 4 bits, then 4 bits. So either there 0 0 1 0 is 2, 1 1 0 1 is 12, 12 is represented by C, 0 1 1 0 is 6, 0 1 1 0 1 1 is 11, 11 is represented by B, 1 1 1 1 is F, and 0 0 1 0 is 2. So the number will be 2C6B.F2 base 16. In this manner, so a binary number can directly be converted into the hexadecimal just by making a pair of 4 starting from the decimal point to the left hand side and from the decimal point to the right hand side, where the left hand side of the decimal is integer part and the right hand side is the fraction part. Now based on the table, system can, okay. Now what we do, how to convert octal number into the binary number. Now the process is reversed. You are given with the octal number and you have to find out its equivalent binary number. The same way we represent. Now each bits of the octal number is represented by its equivalent 3-bit combination. Now the 6, where 6 is represented by 110, 7 is represented by 111, 3 is represented by 011, 1 is represented by 001, 2 is represented by 010, and 4 is represented by 100. Now this number is directly converted from octal to the binary number. And the same process can be done for the hexadecimal number, where each hexadecimal digit or bit can directly be represented by 4 bits. As we require 4 bits to represent a binary hexadecimal number, suppose we have given an example 306.D base 16. So this hexadecimal number is to be converted into the binary number. So what we do, we represent each bit by its 4-bit equivalent binary number. So 3 is represented by 0011, 0 is represented by 0000, 6 is represented by 0110, and D is represented by 1101. D is 13, so 13 is represented by 1101. So this hexadecimal number is directly converted into the binary number. Now when the number systems are completed, we have to move to the next topic, that is the complements of the numbers. Now, complements are the operations used in digital computers for simplifying the subtraction operation and for logical manipulations, that is the logic inversion. There are 2 types of complements for base R system. Here we'll discuss in the generalized manner, and we'll take some examples from each number system. The diminished, the first one is the diminished complement or r minus 1's complement. R minus 1's complement is also known as diminished complement. So for the case of a decimal number, if the base is 10, so we can say the diminished complement of decimal number is 9's complement. For the case of octal number, when the base is 8, so diminished complement will be 7's, r minus 1, that is 7's complement. Now for the binary number, it will be 1's complement. For the decimal number, it will be 9's complement. Now the next type of complement is the radix complement, that is the r's complement. So for the case of binary number, it is 2's complement, and for the decimal number, it is 10's complement. So what we have two types of complements, and complements are used for the mathematical manipulation, or simply when we are going to subtract a number from the other number, then it is done with the help of the complements. The process is very much easy when we are using the complement form. Now first let us discuss the diminished radix complement for decimal number, that is the 9's complement. Suppose given a number n in base r having n digits, the r minus 1's complement of n is defined as r to the power n minus 1 minus n. So r is the base, small n is the number of bits, a capital N is the number in decimal. Now for decimal number, r is 10, r minus 1 is 9. So the 9's complement of n is given by 10 to the power n minus 1 minus n. So we can say that 10 to the power n represents a number of constant number that consists of a single 1 followed by n zeros. Suppose n is 2. So 10 to the power 2 is 100. So 1 and followed by 2 zeros like this. And 10 to the power n minus 1 is a number represented by n nines. We take an example. For example, if n equals to 4, we have 10 to the power 4 is 1, 0, 0, 0, 0, and 10 to the power 4 minus 1 is nothing but 4 nines. So what we are doing here, when we are calculating r to the power minus n minus 1, then it will be an n digit 9 numbers minus 9. So what we are doing, we are just subtracting a number from the n nines. Now it follows that 9's complement of a decimal number is obtained by subtracting each digit from 9. Let us take an example. Suppose we have to calculate the 9's complement of 5, 4, 6, 7, 0, 0. So it is calculated by, here the number of digits are 1, 2, 3, 4, 5, 6. So what we are doing here, 1, 2, 3, 4, 5, 6. So 6 nines minus this particular number represents 4, 5, 3, 2, 9, 9. Or simply if I subtract each digit, then 9 minus 0 is 9, 9 minus 0 is 9, 9 minus 7 is 2, 9 minus 6 is 3, 9 minus 4 is 5, 9 minus 5 is 4. So what we are doing, the algorithm looks like a bit tricky, but what we have to do, we just have to subtract each bit or each digit by 9, and the resultant number is your 9's complement. Now again we have some other examples. Suppose we have to calculate the 9's complement of 0, 1, 2, 3, 9, 8. So what we are doing, we are subtracting each digit by 9. So 9 minus 8 is 1, 9 minus 9 is 0, 9 minus 3 is 6, 9 minus 2 is 7, 9 minus 1 is 8, 9 minus 0 is 9. So either we can directly write by subtracting, or we can just show that how it is obtained.